Seen Invisible Gas, Optical Gas Imaging Theory by me, Vince Couch. I'm a physicist and consultant to Linked Aerial Solutions. Today is July 20th, 2025. Okay, so let me first talk about the relevant physics theory that I've drawn upon to better understand OGI, Planck's radiation law, radiometry and radiative transfer theory, the Beer-Lambert law, Kirchhoff's law, and other laws that are important, the zeroth law of thermodynamics, conductivity, and convection. I'll get into a lot more details about all of this in the next several minutes. Okay, so why can we see during the day but not at night? Question number one. And why are some gases invisible to the human eye? Okay, so the answers to these questions can be found by knowing what light is. Light is a wave composed of oscillating magnetic and electric fields. It carries energy, momentum, and travels at a certain speed. This is something that was discovered by Maxwell in the late 1800s. Light is often described by its wavelength and or frequency, where wavelength measures the distance between peaks. Okay, so here's a peak and here's a peak. So this distance right here is the wavelength. And frequency indicates the number of wave peaks that pass some arbitrary location per unit of time. Okay, so if, say, this is one wave peak from here to here, so this would be one wave. So if that passed this point in 1 second, the frequency would be 1. Okay, if that passed in a half a second, the frequency would be 2. Okay. There are many different forms of light. Visible light, which we can see. Okay, and that's in this range right here, about 0.4 to 0.75 microns. Radio is actually very long. Okay, so that's in this here. So the distance between the peaks for radio could be as much as 100 meters. Infrared, which is what OGI camera sends, is between 1 and 1,000 microns. Okay, the cameras that we use to detect methane and other gases are typically sensitive to 3.2 to 3.5 microns. Okay, so I talk about microns quite a bit. So a micron is 0.000001 meters. Okay, so very, very small amount of length. And if you don't remember what a meter is, well, there's about, it's kind of like a yard. Okay, there's about 3 feet per meter, 3.28, but just three is enough. You want to keep that in your memory. So a meter is kind of like a yard. Why can we see during the day but not at night? Okay, well, they're two very different wavelengths. Our eyes are sensitive to visible light, okay, but our eyes are not sensitive to infrared radiation. Okay, so we can't see that, but we can see this. At night, light in the visible spectrum is not available, right? The sun's not shining, turn all the lights off, and there's no visible light, so we can't see anything at night. However, objects with a temperature are giving off light waves, but it's in the infrared spectrum. Okay, so if you have a camera that can sense infrared radiation, you can see objects at night. Also, there are certain gases, including methane, carbon monoxide, sulfur hexafluoride, ammonia, and many others that are invisible to us. It's because they do not absorb, emit, or reflect light in the visible spectrum, but they do absorb, emit, and reflect light in the infrared spectrum. So that's the trick here, right? Gases we can see with a OGI camera, but we cannot see with our human eyes. How infrared cameras see invisible gases and objects at night. So objects and some gases emit light due to their temperature alone. The chart to the right depicts the wave energy of 5 different objects at different temperatures and wavelengths. Okay, so each one of these is a different temperature. Okay, this is an object at 2000 Kelvin. Okay, so 1000 Kelvin is about 1300 degrees Fahrenheit. Okay, so The models I work with need Kelvin as an input, so I'll constantly help you connect Kelvin with Fahrenheit. So 0 degrees Fahrenheit, right, it's cold. 32 is freezing. So 0 would be 256 Kelvin. 110, right, really hot, would be 316. So obviously this would be super, super hot, in excess of 2,000 degrees Fahrenheit, well in excess of 2,000 degrees Fahrenheit, almost 3,000 degrees Fahrenheit. Okay, so this is hot. So here is different wavelengths. It gives off different amount of radiation. Black body radiation, we call it radiance, but it's essentially light energy. Okay. Um, okay, so different wavelengths, right? It has different amounts of energy. Okay, here is the max. So this wavelength is giving off the max energy. Now, as you can see, some of it's in the visible spectrum. So even at night, if objects get hot enough, you can see them. This object at 1,000, right? That could be a stove, right? I mean, we can heat a stove up to about 1,300 degrees, and that would be about 1,000 Kelvin, and you would see it. We typically see it as red hot. Well, if you turn it up enough, turn up the heat enough, you'll eventually see green hot and blue hot. So that's kind of cool. Okay, but most objects on Earth are between 256 and 316. Okay, again, that's 0 degrees Fahrenheit to 110. So walking around, just looking at stuff, heated by the sun, human bodies, 98.6. They're going to be in this range here. So this would be the closest to what we're typically seeing is going to be 300. Okay, so as you can see, it doesn't emit anything in the visible spectrum. Okay, this is all going to be invisible, but it's visible with infrared detector. Okay, so again, this is visible spectrum, this is invisible. Okay, another variable that affects the amount of light an object emits is its emissivity. Emissivity is measured by something called an emissivity coefficient. And here are several of them. Okay, aluminum foil, 0.03. Okay, if it's highly reflective, like aluminum foil, its emissivity will be very low. Okay. Aluminum and anodized, so that's a different kind of aluminum, but it's got very high emissivity. Okay, human skin's 0.98. So we absorb a lot of heat, we give off a lot of heat. But a lot of this heat's coming from within, right? It's coming from chemical reactions. So we're certainly not a human black body. Everything we absorb from the sun do we emit. If we didn't, we'd be in trouble, right? Okay, so, and then sweat cools us down as well. Ice, 0.97. Even though ice is pretty reflective, I think it's because the surface is so rough. It's got a rather high emissivity. Polished silver, that's highly reflective, so very low emissivity. Gases, including methane gas, also emit and also have an emissivity coefficient. And it varies by wavelength. It can be as high as 0.9 and as low as 0. Okay, so here is pitch dark image using an infrared camera. So there are different intensities of infrared light all around us because all objects have a different temperature and are emitting infrared light. For example, we cannot see the cars in this image here at night because our eyes cannot detect infrared light emitted by these objects. But as I mentioned before, infrared cameras can. Now, again, as mentioned, the amount of light infrared emitted depends on temperature. And chances are these objects probably have about the same temperature, which is why they seem to be about the same color. Objects less warm are going to appear darker. Okay, so the background looks like it's cooler than the cars. Okay, so it's appearing darker. Also, the emissivity, right? Different materials emit infrared light differently. So even at the same temperature, their emittance may be different. So they will look different. For example, glass emittance can be as low as 0.3 and painted metal about 0.8 to 0.9, which is why the auto glass here looks different from the body of the car. Okay, the tires look different as well. So delta T is temperature difference between two objects, okay? So even though the delta T here between the cars is probably pretty low, they're probably almost at the same temperature. The emittance is probably about the same as well. I mean, they do have very similar colors, right? But we can see the geometry of the cars because there is empty space between the cars, and the background temperatures and emittance values of the air is different than that of the cars. Okay, so if the air and say water vapor in the air was at the same temperature as the cars and had exactly the same emittance, then I think it would be very difficult to see the cars. How infrared cameras see? Well, I've mentioned that already. This is a thermal image of me captured using the Sierra Ventus thermal camera. So this is how I look right here in the infrared spectrum. I'm very handsome, as you can see. So even if the lights in the room were not on, I would still appear as this, right? This was taken during the day. Okay, this camera is capturing infrared light primarily between 3.2 and 3.5 micrometers or microns. Okay, my skin has emissivity of 0.98 and is at a uniform temperature, which is why my entire head appears the same color, right? My head all looks the same color because it's got the same temperature, same emissivity. Okay, my glasses appear darker than my head. This is due to the fact that the plastic glasses are at a lower temperature than my skin, and as indicated by the chart on the right, they emit less light energy, right? Lower temperature, right, for a given wavelength. So say this wavelength, this temperature 300, the energy is here. Same wavelength, higher temperature, there's more energy. Okay, moving on. So most objects that will be surveyed with an OGI camera have temperatures between 32 degrees Fahrenheit and 160 degrees Fahrenheit. So 160 is the temperature of asphalt or concrete in 100-degree heat. So it can rise to as high as 160 degrees Fahrenheit. So as you can see, that covers a pretty small fraction, right? This is 300. Right, this is 300. So most of the temperatures we deal with are going to be between 273 and 340. This is 500 here, right? So it's good. So imagine a curve right in this range right here. So we're dealing with a very tiny wavelength band for a curve that only extends from here to here. Is that a problem? So what I decided to do is figure out the range of wavelengths between violet and red, right? The visible colors, violet and red. So this is 0.74 microns, right? This is a 740 nanometers. That's 7.4 times 10 to the minus 9th meters. That's 0.74 microns, and this is 0.35 microns. So the difference is 0.39 microns, right? That's the range of all the visible colors we see. The wavelength range of the mid-wave OGI camera is about 3.1 to 3.5 or 0.4 microns, so it's about the same. So you might say that's a very narrow band, but that's a lot of space, right? We can see all colors with just 0.39 microns difference of wavelength. Here's the thing. Our eyes can detect wavelength differences as well as light intensity differences, but OGI cameras can't. All they can do is detect intensity differences. Okay. The filter will allow in only these light wavelengths, and then thereafter, we're only going to see different colors based on different intensities. Okay, so here is basically this curve right here, light energy curve, but over the very tiny wavelength window we'll be looking at, from 3 to about 3.1 to 3.5 is this range right here. And these different colored lines are different temperatures of either a gas or whatever. And I'm assuming emissivity here is 1. And for the gas in the range we're interested in, it's actually very high. Okay, so here are the three different curves, three different temperatures. So what I did was I added up the total light energy from 3.1 to 3.5 over a temperature of 32 degrees Fahrenheit, which is 273 Kelvin, and I got 0.0132 watts per meter squared. Okay. At 80, I got that's 300 Kelvin, 0.0552. And at 160, I got 0.304. Okay, so those are really small amounts of power, right? And that's what's called isotropically, so in all possible directions. If you want to get it kind of focus on only that perpendicular to the surface, you'd multiply these by pi, which is 3. Still rather small, okay? Now this is something called Stefan-Boltzmann, and effectively, for basically what it's doing is it's taking a particular temperature and it's finding the energy under not just those small band of wavelengths, but all those wavelengths. So the area under the curve under all the possible wavelengths integrated over a hemisphere. Okay. So if you do that with this extraordinary equation, and I divided both sides by 8 to get the same units here because I've got watts over meters squared. And again, multiply that by pi and you've got to get rid of the steradians. Now you're getting 460 watts. Okay, so as you can see, there's a big difference here. And again, it's because we're dealing with very low amounts of light energy because the spectrum is so limited. And therein lies the genius of the cameras. They can detect such tiny amounts of radiation. Okay, so how do we get from light to colors on a screen that we can detect temperature differences for light that's not even visible? Okay, so therein lies the magic as far as I'm concerned. Okay, so here are the components of your typical OGI camera. So the lens here, right, collects the energy and passes it on, focuses it to the detector, effective focus. But it passes this light through the filter. Okay, this is part of the magic. The filter only allows light wavelengths of 3.2 to 3.5 microns in one such very popular OGI camera. Those tuned to look for methane, propane, octane, and a lot of important gases in that range. And then you've got the detector that converts the light energy into a current. And the magnitude of the current is proportional to the magnitude of light energy. Okay, now we can measure currents. And the software does that. The software then converts the electrical current signal to color image. So it's different colors will have different light intensities. Okay, to recap, any object which has a temperature absorbs and emits light primarily within the infrared wavelengths. Gases also absorb and emit light in certain wavelengths. Methane gas, CH4 here, emits and absorbs strongly in this 3 to 3.5 range, as well as water vapor, right? That's going to be the primary constituent in the atmosphere that's absorbing and emitting light. Radiative transfer theory. The primary interaction between gas and light includes transmission of light through a medium. Okay, so this is the graph here, the blue dotted lines. Okay, and this, for those physics and math geeks out there like me, this equation is exponential to the minus KL. Okay, K is a absorption coefficient, which increases with the concentration of the gas, and something called the absorption cross-section, which I'll get into later. So the higher the concentration of the gas, right, the higher this number is going to be, okay? And since this is 1 over exponent of KL, the less this is going to be. So the higher concentration, the less the transmission. And that makes sense, right? Light won't transmit, or will transmit less through a very high concentration of gas versus a very low concentration of gas. L is the thickness of the plume. The larger L is, the smaller transmission is going to be. So thicker plume right, of gas will transmit less light than a very thin plume of gas, or a small L. So for very thin plumes, right, the transmissivity is very high. Okay, so about 1 for, 5 meter plume or 5 centimeter plume. And then as the length of the plume lengthens, the transmissivity through the plume actually drops. Okay, another important relationship is this. So transmission of light through a medium plus reflection plus emissivity is equal to 1. Okay, so this is a law of physics. Now, it turns out that reflection of light, R here, is insignificant for most gases. So therefore, for gases, this simplifies to this. Transmission plus emissivity is equal to 1. Okay. Absorptivity is alpha here, Greek symbol alpha, and emissivity are represented by the brown dotted line here. Okay. For gases at a constant temperature, absorptivity is equal to emissivity, and this is Kirchhoff's law. Okay, so therefore, we can put absorptivity here, replace E with alpha, right, and solve for alpha, and we get absorption is the same thing in terms of value as emissivity, 1 minus the transmission. So what that says is as transmission is high, right, when that's high, emissivity and absorption are going to be low. Okay, so the thinner the gas is, right, the more dilute the gas, the higher the transmissivity, right, in this region. But the lower the emissivity, right? Whereas the thicker gas plume is going to have higher emissivity, right? But you're going to get less transmission through that. So again, this is very important. Transmissivity plus emissivity is equal to 1. So one goes up, the other goes down. And then also you can replace epsilon with alpha here. So transmissivity plus absorptivity is also equal to 1. So the higher the transmission, the lower the absorption. Okay, so the image here was captured by the Ventus OGI camera, and it illustrates methane gas escaping from a tank. Okay, so while this gas is not visible to the naked eye, the Ventus OGI camera is capable of detecting it night or day, right? So if you did this at night, it would look the same as if you did this during the day. Assuming the temperature was about the same. So assuming this thing is indoors, right? Temperatures are about the same. It's going to look the same. And here's what that camera looks like, right? It's amazing. It can do all that. It's so small. We use these at LinkDoc because we can put these on drones. But you don't need a drone to use it, actually. Okay, so leaking gas in the image above can be distinguished from the background for one simple reason. Okay, the light energy arriving at the camera from the gas is different than the light energy from its surroundings or the background. This could be due to the fact that the gas might have a different temperature than the surrounding air or background, and or the gas has a different emittance value, which varies for solids and gases, as I've discussed. So as you can see from my simulation, and I'll show you the assumptions that I use for this result here in a minute. The light energy arriving at the camera from the background, okay, right here. Okay, so this light from the background only passed through water vapor. The atmosphere, again, water vapor is the key constituent, which is absorbing some of this light. Okay, so the amount of light that reached the camera, this is inside the camera now, is only 0.0061 watts. That's 6.1 milliwatts. So that is very, very small. But the good news is the background light that passed through the gas and the water vapor was even less, 0.0026. That's 2.6 milliwatts. Okay. And that's a 57% difference. Okay. And the camera can detect such a small difference, and it will graph these as two different colors. Simulation model. So I built a mathematical physics model to model an OGI camera and its environment, and that's what these next several slides are about. Okay, so here is what I modeled. Down here, I've got storage tank of methane gas, and I'm color blue. And I call this the background light. So lights coming off this tank, BG. The emittance, I'm assuming to be 0.8. Okay. So the background light, okay, so these white arrows, leaves the storage tank and radiates outwards in all possible directions, isotropic. Okay, some light rays will penetrate the plume of gas, and this rectangle here is the plume of gas, and then go on to penetrate the atmosphere to arrive at the camera lens. Okay, so I'm calling this water vapor because that's the main constituent in the atmosphere which will absorb light. And I'm assuming that is 10 meters. Okay, so 10 meters or 100 or 1,000 centimeters. Thickness of the methane gas plume is, I'm assuming 1 meter, so that's about 3.28 feet. Now, some of the light emitted by the storage tank will not pass through the gas, but only make it through the water vapor on its way to the camera. So the amount of light emitted by the background, the water vapor, and gas can be computed mathematically, which has been done by me and via the simulation model. And I'll show you what those values are. So what you have being emitted then is light emitted from the storage tank, light emitted by the gas, which has to make it through the water vapor, and then light emitted by the water vapor. Okay. Therefore, what will arrive at the OGI camera includes light, in this example, of 4 different intensities. This right here is the light from the background that travels solely through the atmosphere. Okay, so that's this one right here. From the storage tank through the atmosphere, on the way to the camera. Light emitted by the gas, net of that absorbed by the water vapor. Okay, so that's this one right here. Emitted by the gas, and some of it's absorbed by the water vapor. Whatever's left over makes it to the camera. The background light, net of water vapor and gas. So here's the background light. Some of it's going to get absorbed by the gas. Some of it's going to get absorbed by the water vapor. And whatever's left over makes it to the camera. And then light emitted from the water vapor is here. Okay. So there you have my simplified model. Okay, so what will arrive at the camera, and these numbers are based on net of the transmission and filter of the lens. Okay, so this is what is going to show up at the sensor of the camera, inside the camera. So as I mentioned, these 4 values, and here are the actual numbers associated with those values. So light from the background, it travels solely through the atmosphere. Okay, so that's right here. That's 0.0061 watts per meter squared. And that is in, if you convert that to milliwatts, that's 6.1 milliwatts. Okay, these are very small numbers, so I'm going to sometimes talk in terms of milliwatts. Okay, so light emitted by gas, net of absorbed by water vapor. Okay, this is emitted by gas, net of that being absorbed by water vapor, 0.0050. This one is the background light, net of water vapor and gas. All right, so that's 0.0026. And then we've got light emitted from the water vapor. Okay, 0.0010. Okay, so in terms of what was emitted by the background, that made it so this ray, in terms of that ray, that's 0.0061, okay, and then the light net of light from the background, net of water vapor and gas, is this ray right here. Okay, so that's where we're going to look at that's going to be the key. We're going to look at the difference between those, the background light that went through the gas versus the background light that went only through the water vapor. I'm sorry, we're going to compare the background gas that went through the gas and water vapor versus the background light that only goes through water vapor. Okay, so So if there's a difference, we'll be able to see it. We'll be able to see the gas. Right, if they were the same, right, if the background through gas and water vapor was the same as the background through water vapor only, the bars would be at the same level. The fact that they're different means there's gas there that absorbed it, or something there that absorbs in those wavelengths of 3.2 to 3.4. And if we know that the storage tank typically has methane, then we say it's methane. If we know that the storage tank typically has propane, then we know it's propane, because propane also absorbs at those wavelengths of 3.2 to 3.5. Okay, so the difference in light intensity actually is pretty significant. Even though these are small numbers, 2.6 milliwatts and 6.1 milliwatts, if you take the difference and divide it by 6.1, you get 57%. It's a very big difference. And we know cameras like the Sierra and others can detect such a small difference. Differences in much, small as milliwatts. Okay, so here's the simulation. You might call it dashboard. These are the values you can change, and it'll automatically generate these graphs and actually many more. And so the most relevant graph is probably the one, it's probably this one right here, background through gas and water vapor versus background through water vapor only. And I'm also including water vapor emission. And this is background through gas and water vapor, gas through water vapor, and then water vapor emission. So this is the total source, the sources through the gas and not through the gas. And you can see here the difference. Then I've got something called a sources and uses, where the light came from and where it went. And here's the net, and that actually ties to this, the light that actually made it through the gas and the water vapor. So this is equal to this. Okay, this is a chart we saw previously. Okay, so here is by wavelength. Okay, these are just totals. This is by wavelengths. This is pretty interesting. So let's look at the from the background through the water vapor only. That's going to be the highest, right? Through the background, it's background light. It's only going to go through the water vapor. So there it is. All right. And it's increasing with wavelength because the output from Planck's equation shows that it increases with wavelength. The next one, the next highest one is from background through gas and water vapor. So that's the green dash line. So as you can see, it drops off pretty significantly here. This is from background through gas. So here you're getting a lot of absorption by methane, right? So it's absorbing a lot in these wavelength bands. So that's why this green line drops. The next is from water vapor emissions. So this is just the amount of light emitted by the water vapor. That's actually pretty low. The emittance of such a slow, a very low ppm of water molecules in the air is pretty low. All right. And then from background through water vapor only is, I'm sorry, we've already looked at that one. From gas emission through water vapor. Okay, so here's from the gas, right? So we know it emits and absorbs greatest in these wavelengths. So that's where you're going to see the most, right? The most light from the gas emission, net of the water vapor. Okay, here's a slightly different chart. This is the background and the various mediums it's going through. So the background light emitted, certainly that's going to be the highest. Here you have an overlap of blue and red, so you can't see the blue. Okay, so that's going to be the highest amount of light emitted from that tank, storage tank. And then the yellow one is background light net of water vapor. Okay, so water vapor is getting some of it, so you're getting a little bit less light at the camera. And then we've got background light through gas. The gas is absorbing more than water vapor, so it's less here, especially at the high absorption wavelengths. And then you've got the dotted line, which is background light through gas and water vapor. Okay, this is going to be a little bit less than the red line because you've also got water vapor absorbing some of that light that was emitted by the background. Okay, so from studying the physics of OGI and running the simulation model I built, I derived several principles of OGI. One is as the concentration, say in ppm, of the gas plume increases and its length extends, there is a decrease in the amount of background light that can penetrate it, i.e. a decrease in the transmission T. Okay, so here's three gases of different concentrations. This is 10,000 ppm, this is 1,000 ppm, and this is 100 ppm. And this is, I've tuned this to a wavelength of 3.11 microns, the light. And so as you can see, for the really high concentration, very little light gets through it. Even at 10 meters, only 20% is making it through it. Actually, this is 10 centimeters. Okay, so very light is getting transmitted through this very dense gas plume. Here at 1,000 ppm, after 10 centimeters, about 80% is going through it. After 100 centimeters, which is just 1 meter, 3.28 feet, only 0.2 of the light intensity, initial light intensity is making it through. Very low ppm 100, even at 2.2 meters, about 70% or so is making it through. Principle: the greater the concentration of the gas plume and its length, the more light it will emit. Okay, so this is relative light intensity. Okay, so at length 0 is 0, right? If I had 0 on the graph, these would all be 0. So even at 10 centimeters, the really high concentration is emitting 0.8. It's relative light intensity is 0.8. 1 would be the maximum that it could be. Okay, so 0.8 after 10 centimeters. That's the depth of the plume. And for this one, this is medium concentration. So 10 centimeters or so, it's emitting about 0.2. Very low concentration. It's not absorbing much energy, right? There's hardly any of it, so it's not emitting much either. Once you get to about 220 centimeters of this plume, say the length of the plume, you can call it the diameter if you want. If you want to call it a sphere, so it'd be the diameter of a sphere of a plume, 220 centimeters, about 0.3 for 100 ppm. So, 100 centimeters of a plume, okay, there's something there. It's going to start emitting light. Okay, so again, the maximum is 1. It's emitting 25% or so of the maximum. Whereas at a really high concentration, the maximum of that object, due to its temperature, is, again, up here, and it's at its maximum. So it hits its maximum at 30 centimeters. 30 centimeters of a diameter of a spherical plume that's emitting its possible max. What about humidity? Does humidity matter? It makes sense that it would. A greater humidity level in the air correlates with an increased absorption coefficient. And so if you have increased absorption, you'll have less transmission. So this is for water vapor. Okay, so humidity is essentially how much water is in the air, water vapor. Okay, so for these wavelengths is when you have, this is humidity of 100%. Okay. And the absorption, 100% humidity, the absorption coefficient's up here. Okay. It's 1.6 times 10 to the 0.04. So it's rather small for water vapor, relatively small compared to like methane. And then at 50%, it's about half. It looks like it's about half of that. Okay, so as you can see, the absorption coefficient is changing with humidity. The more humid, right, the greater the absorption coefficient, and the more light will be absorbed by the air, water vapor in the air. And again, the less light that will be transmitted through it. The more humid the air, the less incoming background light that passes through it on the way from the source of the camera. Okay, so I've already talked about that. This is at 100% humidity. So say you're 1,000 centimeters, that's 10 meters from the gas source. The relative light intensity is at 85%. Here it would be at 1. Okay, so the greater the humidity, the less light that's transmitted at some given distance. So 22 meters, that's about 60 feet. Only about 75% of the maximum intensity will make it through um, the uh, the atmosphere, again, which is water vapor. The more humid the air, the more light it will emit due to its temperature. Okay, so yeah, so the greater the absorption, uh, the greater the humidity, and the more light it will emit. Right. So the water vapor, the denser it is, the the more heat it can absorb, and therefore it's going to turn around and emit the heat that it's absorbed. Okay, here's the delta T simulation. The larger the temperature difference between the gas and its surroundings or the background, the more pronounced the contrast between them. Okay, so this is a simulation model, and this is at the camera sensors. It's accounting for the filter. It's accounting for quantum efficiency and the lens, right? Only certain wavelengths passing through that. Um, so this is net again at the detector or the sensor. Okay. And okay, so the background through the water vapor is light through the water vapor, and then the light from the water vapor emission, 0.0071, and then versus the background through the gas and water vapor, and then you've also got gas through the water vapor and also water vapor emission, right? So that's the total light through the gas, total light just through the water vapor, and here's the difference: 0.00098. Okay. Okay, these are all the same temperature. So background gas and water vapor have same temperature. They have slightly difference in light intensity because their emittance is different. Um, okay, here you've got gases at 305. So gas is a little bit warmer relative to the background. And we see the difference climb from 0.00098, which is 0.98 milliwatts, to that would be 2.1 milliwatts. Okay, so from 1 to 2.1, so that's about a 53% increase. So the temperature went up by 1.7% from 300 to 305, and yet you had a 53% increase in the difference um, in the light intensity. So the more delta T, the greater the contrast. Having said that, you can see here, even though we didn't have any delta T, because the emittance was a little bit less, you still had a little bit of contrast. Okay, so mathematical detail. Okay, so here are the mathematical equations representing the theory of OGI cameras. This is Planck's radiation law, and all you do is you plug in temperature here and the wavelength here, and it'll give you the radiance, the light radiance in units of watts or as meters cubed times the radius. It's a solid angle. Okay, I know that's bizarre and stuff, but tell you what, if enough of you say you want me to do a video on what steradians is, I can do that. Or you can go online. There's actually some good videos on what a steradian is. The Planck integral, I use this, right? Because I'm integrating over 3.1 to 3.5 microns. And that's going to be in units of power over meters squared times steradians. Scene radiance. Okay, so here's the scene. Here's the equation I showed you on the previous page. All right, so this is before we get into the camera. Okay, so this is the image that the camera will see. This is the light energy anyway. The camera will see. And here are my factors. I'll get into these in a bit. Beer-Lambert law, which I've discussed previously. This equation, transmission plus reflection plus absorption is equal to 1. R is typically set to 0, and also scattering, since for gases, R is very small. And then for constant temperature, if a gas is at a constant temperature, the emissivity is equal to the absorption. Okay, so I discussed this image again. Again, this is so important. I thought I'd go into slightly different detail about it. So let's look at one sample here. So what I did was I picked. Let's see, this thing has shifted over. I computed this 0.173, okay? And that's at a temperature of 300. So the red one right here, this vertical line should be more like here. So as I move this around, it's got shifted. So this is for this particular wavelength, right? At this particular temperature of 300, So I plugged in a wavelength of right about in here. I guess this would be 1 micron. This would be, so I think about 6 microns. So I plug in about 6 microns into this equation for lambda, 6 times 10 to the minus 6 here as well. And then temperature, I plugged in 300. And the rest of these are constants. That's the speed of light. That's the Planck constant, Boltzmann constant, K. All right. And I ended up with 0.173 watts per meter squared per unit wavelength. And this is in micrometers. Okay. So that's the number I computed, and it shows up here. Now, if you want to convert that to watts per cubic meter, you convert this by multiplying it by 1 times 10 to the 6 micrometers per meter. And that's where this comes from. The emissivity, I'm assuming, is 1. Okay, that's perfect emitter, black body. Okay, then you can integrate that. That's only this particular wavelength right here, right? But if you want it over all wavelengths, essentially the area under this curve, then you either integrate it yourself, or you can use this wonderful little equation, and this would be P over A. That's emissivity 1. So P over, you're going to bring A over here down here. And then you take the temperature to the 4th power and multiply that by this constant. And now you've got the amount of light energy for the entire temperature of an object at 300, assuming it's emitting at all possible wavelengths, like a solid body would. Gases don't, as you've seen. Solid body would. Okay. Now, this has got pi in it versus this. This is the standard form of Planck. And this just means that this is emitted not isotropically in all possible directions like this is, but perpendicular to a flat surface. Okay, so depending on your application, you may want to use this or this. Okay, so when you do that, so this particular wattage, right, it's this 1.173 watts per meter squared. Okay, over all possible wavelengths, it's 459. Okay. Transmission, absorption, emissivity of light. Talked about this already. So transmission plus absorption equal to 1. True for gases where reflection is minimal. And then Kirchhoff's law says absorption is equal to emittance if the gas is at a constant temperature. So therefore, we can replace A with epsilon here. So transmission plus emittance is equal to 1. Beer's law says transmittance is equal to this exponential. That's e to the negative KL. Right, that's C. So multiply some gas that's incident, say at the bottom of a cloud of methane. Well, by the time it's transmitted through that cloud of methane, multiply it times the exponential of the absorption coefficient times the length had to travel through the gas, and you have the gas on the other side. Okay. Now you take, using this equation, 1 minus T would be emissivity, right? And that'll tell you how much is emitted by the gas plume, water vapor, gas plume, whatever. So this would be 1 minus, not 1 time. I left the minus sign out here. So 1 minus exponential minus KL. Multiply that times Planck's law for the gas, right, of temperature, whatever. And say we've already integrated over 3.1 to 3.5. And that will give you the amount of light emitted. Multiply that amount from Planck's equation times this. Okay, so I've graphed it here. So for methane, this is the transmission at different wavelengths. As you can see, the transmission, it's pretty much invisible, right? Light travels right through it for these wavelengths, 3.5 on. 3.5 to 5. Actually, you go a little bit higher to 7, it'll start absorbing again. But so for wavelengths of methane, for wavelengths of light above about 3.4, 3.5, it'll pass right through. All of it, light will pass through methane. None of it will be absorbed. But in this very tight band here, 3.1 or so to 3.5, you got a lot of it is absorbed. Very little is transmitted, right? So a lot of it's absorbed and it gets re-emitted here, all right? Water vapor, also, it's pretty transparent outside of 3.5 microns, right? But it's got some absorption here, not much. Compared to methane, it doesn't absorb hardly at all, right? It's transmitting at 0.9 here. So, I mean, it's only absorbing 0.1, right? Emission and absorption are equal here. So it's only emitting and absorbing at 0.1. This is another interesting relationship. Reflection plus emissivity is equal to 1. So when reflectivity is high, like a polished metal, right? Say it's 0.9. This would only be 0.1. Emissivity would be very low. Like concrete doesn't reflect very well, so that's why emissivity of concrete something like 0.9. Then you get into this very important absorption coefficient that shows up in Beer's law, right? As well as the emissivity equation. So that's absolutely critical, maybe the most important variable in this analysis. So let's say for a cloud of methane, we want to compute that, and it varies by each wavelength. All right, it's going to vary by each wavelength. It's equal to the molar concentration of the gas, of the methane gas, times the absorption cross section, and that's what this is. This is determined by experiment. So I just downloaded this from a science website. So what is molar concentration? Well, it's defined as the number of moles of the gas times the number of molecules per mole, and that's Avogadro's number. That's 6 times 10 to the 23rd, times the ppm fraction. Okay, that's something we have to input into this model. Okay, so ppm is entered. This is a number, 6 times 10 to the 23rd. How do we get the number of moles of the gas? We use the ideal gas law. Pressure of the gas times the volume of the gas divided by this constant times the temperature of the gas. All right, well, that's easy enough. In this example, right, I'm going to use N is equal to PV over RT, right? So the pressure is 1 atmosphere, so that's at sea level. We're going to say it is 0.001 liters, which is, let's see, that's 1 cubic centimeter. So 0.001 liters is 1 cubic centimeter. So it's a small, relatively small amount of gas. Imagine a cube of 1 by 1 by 1 centimeters on each side. R is just the constant. Okay, so we're going to multiply that out. We get a very small amount of methane, right? That's a very small volume of space. So now we can compute N. We've got each of number of moles. We've got the this constant. We also have the ppm. So there's our N. This is coming from the database or this. Let's see, absorption. Yeah, this is the cross section. So this is coming from here. 2.47 times 10 to the 16th. That's the large N. And this is the absorption cross section from this chart at 3.3 microns. It's about 1 times 10 to the minus 18th. So now we can compute the absorption cross sections 0.0247. Okay, and that's what you plug into this equation right here. That would be your K, and then L is just the distance, right? The length of the methane cloud. Okay, so you've seen this chart. I've gone through this in quite a bit of detail. This is the equation for each step. All right, so the emittance is, all right, the emittance from the tank is this. Just enter the temperature of the storage tank, and then the emittance, right? And for a storage tank, the emittance is constant over all wavelengths. And then the rest of these are constant. And then I'm integrating this wavelength from 3.1 to 3.5, okay? So that's easy enough. And then here, the light emitted by the background absorbed by the gas. So I'm measuring the absorption here. Okay, so the absorption, light emitted by the background, absorbed by the gas. Yeah, so remember, emittance and absorption is the same, right, for constant temperature. So 1 minus T. And T is exponential of KL, where K is the absorption coefficient for the gas, okay, multiplied by I. Light emitted by the gas, right, is also the emittance and absorption are the same. So we're minusing this because it's been absorbed. This is emitted by the gas, so it's 1 minus exponential absorption coefficient of gas times the length of this plume times, this is from Planck, right? This right here, this is from Planck. So that's what we're doing all the way up. We're getting the emittance. This is the emittance of light by the water vapor, okay? Light absorbed by the water vapor from the emitted gas. So I take all these. These are the absorbed, the minus alphas. And the emittance is the epsilons, the plus. And I add them all together, okay? And I end up with this equation right here. Okay, this is the absolute key equation in the simulation. Okay, but that's getting out. You're right outside the camera here. To get inside the camera, you got to go through the lens and the filter and the camera mechanism. So these are the factors. So it's not going to let all of this light in. Okay. And this varies by the camera and the manufacturer. So I was able to get this information from a manufacturer of one of the very good cameras to run my simulation. But I can't give you more information than that. That's confidential. And that's basically it. It's fairly remarkable. It's quite a bit of mathematics and physics to get basically get the pixels right, and all that math. And what are we getting out of it? Let me show you again. We're getting 4 pixels, right? Now, I had to simplify this, right? I simplified this to one source, two source, three sources, right? Two mediums and three sources. Now, in the real world, right, you've got light coming from everywhere, right? And dozens of different objects. You really only have one water vapor and one gas cloud. So that's good. But you have a lot of different sources. So you're going to see a lot of different colors here. But you'll know this is gas because it'll be moving like gas, right? It'll look different. It'll have a different color, and it'll also be kind of moving like smoke. All right, so that's all I have. The last thing I did here is what if we allow the temperatures of all the objects to be the same? All right, so each of these i's would be I sub 0. They'd all have the same I, right? And then we add it all up. What do we get? We get one color, and that's the light that came off of each one of them, right? You just they all, it all goes back to here. This cancels that. This cancels that. And what you're left with was the emittance of light, which is the same for each object. You're just going to see a white screen, right? So if the temperatures and the emittances of everything, including the background, are all the same, you're just going to see a white screen. Okay, that's why you need some delta t between the surroundings and the object and or emittance differences.